requiring a year of 365 and a quarter days to complete one revolution. Moving still closer to the Earth, we see its satellite, the Moon, revolving about it. This is the only satellite used for navigational purposes. This, then, in general, is the way our solar system appears from space. However, as people live and travel on or close to the Earth's surface, they can view the heavenly bodies only from the Earth. Therefore, in the science of navigation, it is convenient to assume that the Earth is at the center of the universe, and that about the Earth is an immense sphere called the celestial sphere, which has a radius of infinity. So immense is this celestial sphere that the Earth, or in fact even the Earth's orbit, can be considered a point at the center. From the Earth, then, the sun, moon, planets, and stars, regardless of their distances from the Earth, appear to be located on the inner surface of the celestial sphere. To show the relationship between the Earth's coordinates and those of the celestial sphere, let us expand the Earth so that it may be plainly seen. We extend the poles of the Earth until they intersect the celestial sphere. This locates the north celestial pole and the south celestial pole. Expand the plane of the equator until it intersects the celestial sphere, and the line of intersection is the equinoctial or celestial equator. In the same manner, we expand the plane of a meridian to the sphere, and it forms, at the line of intersection, a celestial meridian. The point directly over an observer's head on the celestial sphere is called his zenith. If an observer is standing at the north pole of the Earth, his zenith is here and coincides with the north celestial pole. As the observer moves southward, his zenith moves along his celestial meridian. When he reaches the equator and then moves westward, observe his zenith moving westward along the equinoctial. So we see that an observer's zenith is always directly above his head. That half of the celestial meridian from pole to pole, which includes the observer's zenith, is called the upper branch of the meridian. The opposite half is called the lower branch. A line connecting the zenith and the observer, projected through the Earth until it intersects the celestial sphere on the opposite side of the Earth, locates a point called the nadir. In other words, the nadir is 180 degrees from the zenith and lies on the lower branch of the celestial meridian. To locate the celestial horizon, pass a plane through the center of the Earth, which is also the center of the celestial sphere, so that it is perpendicular to the zenith nadir line. The line of intersection of this plane with the celestial sphere is called the celestial horizon. The relationship of the horizon to the zenith nadir line is similar to the relationship of the equinoctial to the north-south axis. Now let us examine the motion of the heavenly bodies on the celestial sphere. The Earth, we know, rotates on its axis in this manner from west to east. This is the real motion of the Earth. However, as we are located on the Earth, we are not conscious of this rotation. Consequently, it seems to us that we are motionless in space and that the bodies on the celestial sphere appear to rotate about us from east to west. This is the apparent motion of the heavenly bodies with which we deal in navigation. As the stars apparently move from east to west around the Earth, observe the circular path they follow. These paths are called the diurnal circles of the bodies. Note that these are small circles of the celestial sphere, similar to the parallels of latitude on the Earth. Now that we have examined the apparent motion of the bodies from outside the celestial sphere, suppose we consider the motion as seen by an observer standing at the North Pole of the Earth. If he looks up at his zenith, he will also be looking at the North Celestial Pole. He will see the stars apparently move in concentric circles about the pole. If, however, he looks to the south, the apparent motion will be parallel to the horizon, because the horizon and the equinoctial coincide. When the sun is in north declination, the sun is always above the horizon at the North Pole. That is why the days are 24 hours long during its summer. And, of course, when the sun is in south declination, it never rises above the horizon, and the nights are 24 hours long. At the poles, the stars do not appear to rise from the horizon and set behind it, as they do in other latitudes. Now let the observer move south to the equator. Here his zenith lies in the equinoctial. If he looks to the north, the apparent motion of the stars will be like this. If he looks to the south, it will be like this. Note that for this observer, the poles of the celestial sphere lie in the celestial horizon. If he looks to the east, the stars will apparently rise vertically from the horizon in this manner, and then move across the sky to set in the western horizon. Their diurnal circles are perpendicular to the horizon. From the equator, the observer would, at one time or another, be able to see all the stars in the heavens. However, when the observer is in some position between the equator and the poles, different conditions exist. In this latitude, he sees the North Celestial Pole in this relation to his horizon. Remember that the line between the zenith and the observer is always perpendicular to the plane of his horizon. The bodies traveling about the North Celestial Pole appear to rise to the eastward and move along their diurnal circles and set to the westward. Note that a star close enough to the pole will not disappear below the horizon and, therefore, does not set for an observer in this latitude. A star so located is called a circumpolar star. In northern latitudes, the North Star, Polaris, is such a star. Looking to the southward from this position, the stars appear to travel in this manner. If the South Celestial Pole, which is below the horizon, is indicated in this manner, we can see that there are some stars which never rise above the horizon. They, therefore, will never be visible in this latitude. Now, if we look to the eastward, note that the diurnal circles of the stars are neither perpendicular to nor parallel to the horizon, but make an oblique angle with it. This angle varies with the latitude of the observer. To sum up this apparent motion of the celestial bodies, observe this diagram. We will keep the horizon in a horizontal position, which will maintain the line from the observer to the zenith, vertical. Therefore, as the observer moves south, we have to rotate the celestial sphere to keep it in the correct relative position. Observe paths of the stars in their diurnal circles. Note the bodies that are below the horizon and which, therefore, could not be seen by the observer. Stopping in a northern latitude, observe the difference in length of time the star A and the star B are above the horizon. When the sun is in this declination north, it is summer in the northern hemisphere, and the days are longer than the nights. But when the sun is in this southern declination, it is winter, and the nights are longer than the days. Now, continuing southward, we reach the equator, and then proceed to the South Pole. Here the zenith coincides with the south celestial pole. Returning to a view of the celestial sphere from outer space, we pass half a great circle from pole to pole through one of the bodies. This half of a great circle through the body is called the hour circle of that body. Note how the hour circle travels with the body. Hour circles are important, as hour angle is measured from a meridian westward to the hour circle through a body. Hour angles are designated in one of two ways, depending on the meridian from which they are measured. When they are measured from the Greenwich meridian, they are called Greenwich hour angles, or GHA. When the observer is on any other than the Greenwich meridian, the hour angle is called local hour angle, or LHA, because the observer's meridian is always called his local meridian. The Greenwich hour angle is especially important because it is one of the coordinates by which a body is located on the celestial sphere. It is similar to longitude on the Earth, except that the Greenwich hour angle is always measured from the Greenwich meridian westward to the hour circle through the body from 0 to 360 degrees, instead of east or west from 0 to 180 degrees, as longitude is measured. Another coordinate used to locate the position of a heavenly body is declination. This is the angular distance of the body north or south of the equinoctial. It is analogous to the latitude of a position on the Earth. Like latitude, it is named north or south. Because of the great distance of the stars from the Earth, their declinations change but little. On the other hand, the sun, being relatively close to the Earth, has a comparatively large change of declination over a short period of time. To illustrate the reason for this, let us consider again the true relationship of the Earth to the sun. We will indicate the plane of the Earth's orbit in this manner. Now, since the Earth takes 1 year to complete its real motion about the sun, it will therefore take the sun 1 year to complete its apparent motion about the Earth in the plane of the Earth's orbit. Now extend the plane of the equator from the Earth, and we can see that this plane is inclined to the plane of the Earth's orbit. This inclination is about 23½ degrees. To turn to apparent motion on the celestial sphere, we move the plane of the equator, which you remember is also the plane of the equinoctial, to a horizontal position. At the same time, let the Earth occupy its position at the center of the celestial sphere. Watch the sun apparently moving around the Earth and observe its path projected on the celestial sphere. This is the apparent motion with respect to the Earth's orbit, and the sun takes 1 year to complete this revolution. The path of this apparent motion of the sun is called the ecliptic. It has nothing to do with the apparent motion caused by the daily rotation of the Earth. The path followed by the sun, because of that motion, is called a diurnal circle. Note that at this point in the ecliptic, the sun is apparently about 23.5 degrees above the equinoctial, or its declination is 23.5 degrees north. And at this point, 180 degrees away, it is below the equinoctial by the same amount and has a declination of 23.5 south. When the sun is in this point on the ecliptic with a declination of 23.5 north, it is the June solstice. This situation occurs about June 21st. When the sun has declination 23.5 south, it is the December solstice, which occurs about December 21st. As the sun apparently moves to the eastward from the December solstice, note that its path, the ecliptic, crosses the equinoctial. This point of crossing is called the March equinox and was named the first point of Aries by the ancient astronomers. The sun reached this point in the ecliptic about March 21st. The March equinox is very important to navigators as it is used as a point of origin for measurement of coordinates. This sign is used to denote the March equinox. The declination of the sun changes at this point from south to north. The point where the ecliptic crosses the equinoctial on the other side of the celestial sphere, 180 degrees away, is the September equinox. At this point, the declination of the sun changes from north to south. Between the hour circle through the March equinox and the hour circle through this star is this angle called the right ascension of the star. It is always measured to the eastward from the March equinox to the celestial body in hours, minutes, and seconds. While the Nautical Almanac tabulates right ascension of stars, the Air Almanac tabulates a function called the sidereal hour angle of the stars. The sidereal hour angle is the angle measured to the westward between the hour circle through the March equinox and the hour circle through the celestial body. It is similar to other hour angles in that it is measured to the westward in degrees, minutes, and seconds of arc, but differs from them in that sidereal hour angles do not change materially, and that they are always measured from the hour circle through the March equinox. It can be seen that if the right ascension is converted into degrees, minutes, and seconds of arc, and this angle subtracted from 360 degrees, the result will equal the sidereal hour angle of the celestial body. It is important to know about the sidereal hour angle of a star because the Greenwich hour angle of a star is equal to the sidereal hour angle of that star plus the Greenwich hour angle of the March equinox. The Air Almanac tabulates the Greenwich hour angle of the March equinox and the sidereal hour angle of the stars commonly used in celestial navigation. Thus, the Greenwich hour angle of a star can be conveniently computed. To sum up, we have learned two ways to locate the position of a heavenly body on the celestial sphere. In relation to the Earth and its coordinates, it can be located by its Greenwich hour angle and declination. If, however, we want to locate them with respect to each other on the celestial sphere, we must use right ascension and declination, or sidereal hour angle and declination. The ancient astronomers in their nightly study of the heavens discovered and recorded these important relationships among the bodies of the universe. Now this science has been adapted to the use of navigators, so that by the sun, moon, stars, and planets, as they follow their ordained paths in the heavens, we may chart our courses on the surface of the seven seas.